Good morning, everyone. I was asked to talk today about Agile architecture and design. This is ThoughtWorks is a company that does a lot of Agile development, and we spend a lot of time thinking about this and discussing this. So that's what I'm going to be talking about this morning. I'll talk about aspects of both of these things, architecture and design, and talk about building architectures for change and delve into some of the reasons why it's difficult to build architectures that are easy to change. But I'm going to start with the poetry of Donald Rumsfeld, who very famously said, "There are known unknowns." That is to say, there are things we now know we don't know, but there are also unknown unknowns. There are things we do not know that we don't know. And he didn't realize it, but he was really talking about software when he said this, because this is the killer thing in software. It's not the known unknowns, because you can make contingency plans for those. You know, I know we're going to have some concurrency there, and so we're going to reserve some time to think about that. The thing that always nabs you in software are the unknown unknowns. Those are the things that you cannot possibly make contingency plans for, and those are the things that always end up ruining your day. And so for a long, long time in the software world, we were trying to treat it like other engineering disciplines where we want to build a lot of predictive power using mathematics and other techniques to try to get better and better at predicting the future. And it turns out what we discovered was not a lot about architecture, but what we figured out was the future is really, really hard to predict. And instead of spending more and more time and effort trying to build a better and better crystal ball, why don't we focus instead on making it less expensive to make changes? And the things that are really expensive in architecture, if we can make those things way less expensive, then we don't have to predict the future. We can react to the future and actually build architectures that evolve along with our problem domains. And a lot of the way that happened in the Agile world was to focus on proven practices. And in fact, a good exemplar of this are the extreme programming guys. Because when extreme programming came about in the early 90s, all the people who were involved in building the ideas in extreme programming had been on lots and lots of other software projects, and they were kind of depressed because it seemed like it was almost random chance when you started a project regardless of which process you used, it seemed like almost a random chance as to whether that project would be a success or not. And so they took a step back from process and said, let's just focus on practices. And let's take practices that we know worked well on projects and just build software around these proven set of practices. So they noticed, for example, that on projects where they were aggressive about testing, they had a higher quality code, and there seemed to be a good correlation between the amount of testing and the quality of the code. And so they said, what's the most extreme version of that? We'll do test first development and write tests before we write any code. That guarantees that all of our code has tests. The most extreme version of that was they noticed that on projects where they did code reviews tended to have higher quality code, and there seemed to be a correlation between the number of code reviews and the quality of code, and so they came up with ideas like pair programming, which is really real-time code reviews. And so they focused on things that you can prove work. They really applied the scientific method to software development, and that's exactly what we try to do in the Agile architecture and design world, is not get caught up in metaphorical comparisons to other kinds of engineering, but focus on things that actually work in this universe. And so let's talk for a second about traditional versus Agile architectures. In the traditional role of architect, as time goes by, you spend a bit of time up front learning about the problem that you're trying to solve, and then in the ideal world, you have all that knowledge and it carries on through the life of the project. But that's not what really happens. You spend a bunch of time up front coming up with a nice structure and how everything fits together, and then at some point the real world very messily invades your really nice plan, and so this nice continuum of design becomes this very fractured, tactical approach to, oh, we didn't anticipate that, we need to now design around that, and we didn't anticipate this, and so it becomes a lot bumpier. In the Agile architecture role, we don't have the luxury of spending so much time up front building all those assumptions and abstractions. And so what we do is try to gradually build knowledge over time, building up more and more over time. And so what ends up happening in the real world in Agile projects is you start building knowledge and you keep sort of building knowledge, but it's kind of rocky along the way, but you need to be able to change and evolve as you go along. And so you're tending toward the right direction, even though it's not a completely smooth curve. You have to spend some time refactoring and making a few changes along the way, but that's anticipated and normal in this kind of world. So there are some consequences of having a lot less time up front. As an architect in an Agile project, you need to have a really good feel for current events. We're big advocates of hands-on architects because you really need to be able to see the shifts that are happening in the code base in real time, because important design and even architecture decisions are happening all the time because you didn't spend a lot of time up front working on those things. So it's really important to be a hands-on architect. It's also important to be able to switch from the micro view of code to the macro view of the entire world very easily, because you'll need to spend time in code, but you also need to think about the big building blocks of the application, how the components fit together, and what the dependencies and coupling between those things are. You also tend to get fewer boat anchors. This is the boat anchor anti-pattern, which says that this is a well-known anti-pattern that's on the C2 anti-patterns wiki. That is, we spend a lot of money for this piece of infrastructure, and so you have to use it on every project, whether it makes sense to use it on this project or not. A lot of times you end up with this because of big design up front. You have this enterprisey framework that everyone's supposed to use on these projects. If you don't spend all that time up front, a lot of times you're able to dodge boat anchors a little more efficiently. Now, the title of this talk is about Agile architecture and design, and so I want to talk for just a few minutes about design, and then I'll flip back over to architecture. So let's talk about design, and in fact, the interesting thing in the Agile world are these topics about emergent design. How can you derive design from things that are already there or things that are just coming into being? There are two definitions of emergent that I'll steal from Webster's. One says rising or emerging out of something that covers or conceals it or coming to light. And the other definition is something that suddenly appears or arises unexpectedly and calls for prompt attention. These two different definitions loosely correlate to the two different aspects of emergent design that I will talk about here. And here's the first one. Let's say that you have a problem at work that conceptually is like this. It's just a tangled mess. And you think about this while you're at work. You think about this while you're driving home. You think about this while you're mowing your lawn. And when your spouse is talking to you and you're supposed to be paying attention to them, there's still a background thread that's kind of working on this problem that you're trying to resolve. And you eventually think about this long enough and have enough insights into it that it resolves itself into some sort of structure that makes sense. This is this exercise of finding abstractions and patterns that already live and exist inside your code. And I'll show you some concrete techniques using metrics to do this in just a second. This is an important aspect of Agile architecture and in particular design, because you need to be able to go and effectively refactor your code and find useful abstractions that are there so that you can take advantage of them and reuse them. And the example I'll give you in a second allows you to eliminate lots and lots of duplicated code once you've identified one of these things. So that's one aspect of emergent design. The other aspect is this idea of the last responsible moment to make decisions about things. And I already sort of alluded to this aspect of emergent design in the picture that I showed earlier, because the idea behind this is for every important decision you make, you ask yourself the question, is there a safe way I can defer this decision a little bit longer? Because the longer you can delay, the more chance you have to have gathered relevant data about the decision that you're trying to make. One of the tricky things in software is you're very often asked to make the most difficult, nuanced decisions at exactly the time you have the least amount of knowledge about the problem that you're trying to solve, which is before you've written anything. That's a really tricky thing. We're trying to get away from that. We're trying to build all of our decisions on data. Even if it's incomplete data, we want actual data as much as possible to base decisions on. So both of these aspects are very common in emergent design. I want to focus on this finding abstractions and patterns business and give you an example, a concrete example of some techniques that we use in the Agile world to find stuff like this. And so let's talk about finding and harvesting an idiomatic pattern. So let's say that I have this code. What this code does is not all that important. This is actually some code from a little toy e-commerce site, and this code takes things out of a shopping cart and puts it into an order using low-level JDBC. And I would like to be able to see if there's some useful, reusable code in there, but I can't because it's just a big pile of code. In fact, I've actually compressed this code a little bit to get it to fit on this slide, but when this slide, before I compressed it, there were big chunks that had blank lines in between there. Like there was a blank line right there, and there's a blank line right there. So it's a really common practice for developers to put blank lines within methods to kind of delineate chunks within a method. How many people do that? You have blank lines within your methods. Everybody does that. You know what that blank line inside that method is? It's a cry for help, to make me my own method. You've already set it apart from everything else in that method. All you need to do now is give it a real name so that you've got a fighting chance of actually understanding what that magical chunk of code does without having to read those 4 or 5 stupid lines every time you need to understand them. And so that's part of the motivation behind the style of refactoring is take the similar things and bunch them together, which you've already done with all these blank lines you've got in your code base. So what I'm going to do is take this code and look at the things that kind of belong together, just kind of scoop them up and do an extract method, refactoring, and get to this intermediate state here. Now, there's a weird side effect going on here, because your refactoring tool has a really, really strong contract with you that says, I will guarantee that your code will continue to work when I'm finished doing my work. Your refactoring tool cannot make decisions about making things class level versus local variables because that has scoping and threading implications. And the only thing it can do in this case, because I have all these local variables here, is to pass all these guys as parameters. When I build up, set up transaction state 4 is 4 or 5 lines of code, and the only way I can do that is to pass these parameters. So this is a common side effect of doing a refactoring in a complex method that has some local things defined. But as a human, I know when it's safe to escalate the scoping of those things so that they can be seen from a broader place and get rid of these local declarations and clean up this code a little bit more. So I want to do another refactoring run on this and end up here. And now I'm actually getting somewhere because now I can see the structure of the code. It does some setup, it does some specific work, it completes things when things go well, rolls back when things break, and cleans up when we're done. And in fact, if I go in here and knock out these 2 very specific lines of code, I now have a template for kind of reusable data access that handles all the JDBC plumbing stuff for me. The inspiration for this style of coding comes from maybe a surprising place from the book Small Talk Best Practice Patterns by Kent Beck. This is what he calls the composed method style of coding, where every public method reads like an outline. And every outline element is a private method that makes that outline section come true. And that's a really nice way to organize your code because all your public methods become these really short summaries of what's going on. And if you really need to see those details, every modern IDE lets you hold down the control key and click on that method name and literally browse into that definition if you really want to see those details. But this hides those details from you when you don't want to see them, and so this makes a much nicer structure. And now, of course, I can apply a gang of 4 design pattern, something like the command design pattern, and completely abstract this and pass that in as a parameter, and now I've built some reusable code. And in fact, I've built some code that is reusable out of a pile of code where you couldn't really see any reuse before. But let me show you another example of this. I want to go and find one of these things out in the wild, one of these little idiomatic patterns that live in your code that you haven't discovered yet. But to do that, I need a couple of metrics. So I'm going to introduce a couple of metrics here that you probably are already familiar with. One of them is the metric cyclomatic complexity, which measures the complexity of a method or a function. This gives you a numeric value for how complex a method or function is, allowing you to compare 2 functions together to see which one's more complex. Thomas McCabe came up with this formula a long time ago, and here's the formula. Edges minus nodes plus 2, where nodes are lines of code and edges are possible pathways through that code. And so if you apply this formula to a real little chunk of code like this, and you draw out this edges and nodes view, you can count them up. 4 minus 4 plus 2, so the cyclomatic complexity of this little method is 2. But it's kind of boring when the numbers cancel each other out like that, and so let's look at a slightly more complex version. This is a more complex method, and you can draw it in this kind of edges and nodes view, and then count things up. And it turns out 8 minus 7 plus 2, the cyclomatic complexity of this guy is 3. So this is one more complicated than the other method. This is a really handy tool because this lets you go and find the most complicated method or function in your entire code base if you want. There are also some interesting derived metrics from cyclomatic complexity, like cyclomatic complexity per line of code as a way of measuring technical debt as an interesting application of this particular metric. And so this will let me go find really complex stuff. So if I'm going and hunting for things within code bases that might be broken, complicated things are really good things to find. The other thing that I want to find are really important things. And there's a metric for that too around coupling. This is a really important metric for architects because it tells how things are coupled to one another. In fact, in a lot of ways, architecture is this tension between cohesion and coupling in a lot of places. And there are two kinds of coupling we care about: afferent coupling and efferent coupling. Afferent coupling are incoming connections to some code artifact, and that may be a class or a package or namespace. And efferent coupling are the outgoing connections from that class or code package or namespace, that artifact. An easy way to remember this is that efferent starts with an E, and that's the first letter in the word exit. So those are outgoing references to something else. And the afferent coupling are the incoming references. The one here that I really care a lot about is afferent coupling, because in many ways, afferent coupling tells us the most important classes within a code base. Because if most of the classes reference this one class, then changes here are going to have a ripple effect, and so that's a pretty important class. And so I now have two metrics, complexity and afferent coupling. What I want to do is go find important, complicated stuff. Because that's the really interesting stuff in code bases very often, are the important, complicated things. So what I wanted to do to test this theory out was to take an existing code base out in the world that everyone's familiar with, that's been around for a long time, and apply these metrics and see if I can find some interesting design issues that have been unresolved for a while. And I decided for my victim, for this exercise, to choose struts. It's been around for a long time. It's a very popular open source web framework. It's in a second major version. So I downloaded the source code for struts, downloaded a simple little metrics tool called CKJM. This is a little tool that runs the Chittimer and Kimmerer object-oriented metric suite on code bases, and it has the two metrics I want, which are cyclomatic complexity and afferent coupling. This particular tool, when it measures cyclomatic complexity, it only measures things at the class level, and so when it reports cyclomatic complexity, it's giving you the sum of the cyclomatic complexity of all the methods in the class. So here's the result of running CKJM against the struts code base. And if you look for the most complicated thing in all of struts, it is this class called double list UI bean, which has a weighted method complexity. That's what it calls this metric. This is the sum of all the cyclomatic complexity of all the methods in that class of 66. So that's the most complicated thing, that and its friend, an abstract double list tag in struts. And so you might think, well, if I really want to make improvements here, I should go attack that thing with gusto. But you look across, its afferent coupling is only 3, which means it's only used by 3 other classes, which means that if I make big improvements here, that really won't ripple out to a lot of other places because it only directly affects 3 other places. Now, it may indirectly affect a lot of other places, but it only directly affects 3 others. What if I sort these instead by importance? Not surprisingly, component is the most important thing in the struts universe because it is a component-based web framework. But what I'm really interested in hunting here are high combinations of numbers. I want to find really important classes that are also very complicated because I suspect that that complexity might be at least partially accidental complexity and not essential complexity. And so I find by digging around through UI bean, that's the one that catches my eye, which has a 53 and a 22. I find by digging around in that guy, this particular method called evaluate params. And I don't have Jeopardy music, but just imagine Jeopardy music in your mind as we look at evaluate params. My very favorite part of this method by far is the very last line of this method when we finally get there. It says evaluate extra params. So it's almost like the developer just got tired of typing at some point. It's like, oh, I just can't type anymore. Okay, evaluate extra ones. Okay. So what this code does is, Struts is a web-based framework, and it harvests parameters and decides what to do with them. Sometimes it does special things to them, like harvest them as form parameters. Sometimes it just filters them and passes them through. So there's a lot of complicated code around handling those parameters. So I started digging around in other classes within the Struts code base to look to see how often this method or family of methods showed up. You can do this in an IDE, but I did it from my command line since I've got pretty good command line judo. From the base of struts, give me all the Java source files and then tell me which ones have an evaluate something params method in them. I have found an idiomatic pattern in struts. And I think this is a good example of these little hidden idiomatic patterns because 15 years ago, 20 years ago, when they started working on struts, I'm sure no one said, you know, the most complicated thing in 15 years in the struts code base is going to be how we handle URI parameters. It's so simple, they've solved this problem over and over and over and over again. Now, I wrote this whole thing up as I wrote this article series for DeveloperWorks called Evolutionary Architecture and Emergent Design. And I wrote this whole thing up about struts as part of that article series. And one of the struts committers contacted me and said that he had independently just discovered the same thing and was in the process of fixing it in what I think is the proper way, which is once you've identified this thing, extract all this parameter handling stuff as an embedded framework inside struts. And so now, that's the way it works, and by doing that, he killed off hundreds of cyclomatic complexity points and thousands of lines of code, simplified the code base, but left the functionality exactly the way it was before, because he found a design element that had been kind of smeared across the entire framework. No one had ever looked at it through that particular lens to be able to see that thing, but once you see it, it's relatively easy to fix that and improve the overall world that you're living in. There's a strong impetus out in the world to try to build frameworks, but we actually don't like to build frameworks if we can avoid it. We much prefer harvesting frameworks out of things that already work. The harvested frameworks tend to be better because you know they have solved real-world problems in realistic ways, whereas built frameworks, if very smart people go to an ivory tower, they can come up with some really cool stuff, but until it has really hit the crucible of real development and real problem solving, we don't think it's as high a quality. So we tend to try to harvest frameworks rather than build them, build it, and then harvest the good parts to build the next thing. So those are all elements of emergent design. Let's talk a bit about Agile architecture and a bunch of issues around that. Architecture really has three different aspects. I'll just talk about two here, but there are really three important aspects in architecture. There's application architecture, there's enterprise architecture, there's also integration architecture, and there are very specific practices around each of those kinds of architectures. But all three of them suffer from the same thing, from my observation, and that is that yesterday's best practice becomes tomorrow's anti-pattern. We very often build architectures around constraints that disappear once we've built the architectures, and then those constraints remain in place forever. You see this all the time. In fact, I can't really tell you anything about what your architecture is going to look like in 5 years, but if history is any judge, it's going to look way different than it does now. So what that suggests is we need to get better and better in the architecture world of embracing change and allow architectures to change, which is a really handy thing to say, but how do you actually get that to work? Because it's difficult. Architecture is the underpinnings and building blocks for all the other things that sit on top of it. So let's talk about ways that you can make that happen. And one of the key things that makes architectures hard to change is coupling. Back to this idea of coupling again and tangling. Rich Hickey revived this fantastic word called complect. There's a keynote that Rich Hickey, he's the creator of Clojure, did, and I'll show you a link to this in just a second from the Strange Loop conference. There's this really old word called complect, and to complect something is to interweave or entwine. It's from this old Latin word complexity. And in this keynote, Simple Made Easy at the Strange Loop conference, Rich did a talk about complecting. And this is actually a picture of complecting that figure 6 here is obviously much more complicated than figure 1. And in the software world, we really want figure 1, but what we end up with very often is figure 6 because we end up complecting things together for various reasons. So I want to talk about 4 different ways that we complect things and we can pull things apart. This is one of the keys to building evolvable architectures, is to be able to untangle things that shouldn't be tangled together because that adds combinatorial complexity. So the first one I'll talk about is this. This is a really common thing in virtually all of our world, these CRUD operations against databases. So we have a relational database and we do updates and reads from the same database. And there are tremendous amounts of complexity built into that. We have object relational mapping frameworks that have almost good enough fidelity to work all the time, but not quite. And so you're always having to hack around the edges of them. I'll talk more about that problem in just a little bit. That's actually a problem of Dietzler's law. But a lot of the complexity that you end up with here is because we're trying to do both those things on top of the same relational store. There's an alternative to this out in the world called CQRS, the Command Query Responsibility Segregation architectural pattern, which breaks those two things apart. You basically have 2 different logical storage facilities. You have one that reads and one that writes, and they slowly synchronize each other in the background. So you've separated the query part from the command part, command query responsibility segregation, and each of those 2 parts can be a lot simpler. A lot of architectures look like this now because now you can just focus on building the best read model possible and the best write model possible, and then making sure that those things get synchronized in the background. This has some interesting implications. This tends to be not a transactional world, but an eventual consistency kind of world. But that's okay because most of the world is moving to an eventual consistency kind of world. I think we did a huge disservice when we explained transactions to users because they got really excited about transactions. And virtually nothing in the world actually acts like a 2-phase commit transaction in the computer world. There was a famous article a few years ago by Ian Robinson that Starbucks does not do a 2-phase commit. Have you ever noticed that? Starbucks is not a 2-phase commit. You hand them their money and you don't have anything to show for that, and that transaction may fail at some point, and you got to talk to somebody. People always model bank transactions as the exemplar of transactions, but no bank in the world actually does a 2-phase commit at an ATM because nobody wants to stand in an ATM for 4 or 5 minutes while it calls some stupid mainframe to figure out if you've got enough money in your account or not. In fact, banks predated computers. And you know, bank records used to travel by the Pony Express, and there is no 2-phase commit when there's a horse involved. So we've gotten our users really used to this idea of transactions, but the real world almost never works like that. Everybody does eventual consistency and then auditing after the fact to make sure things work. And so this reflects the more realistic constraints of the real world in a lot of cases. Of course, this won't apply to every architecture you have, but if you have the ability to do this, suddenly the really complex parts of your architecture become much simpler because you've split those things apart. You've untangled those 2 things. Another big example of untangling, and I'll give you several examples from this untangling in this world, is from continuous delivery. It's hard to talk about Agile architecture now without talking about continuous delivery as well, because continuous delivery is really a whole bunch of engineering practices that support these ideas that I'm talking about from an architectural standpoint. But part of the problem with continuous delivery is we officially have too many things in the Agile world with the word continuous in the name, and it's getting kind of confusing. So let's talk about what each of those continuous things are. And I'll start with the first one, which is continuous integration. This is one of the things that the extreme programming guys started. This is another one of their observations that they made in the early days of XP, was that on projects where they did integration more eagerly, they had fewer integration-based problems, and the more they put it off, the more painful it was. And so their idea was, let's do continuous integration, which says everybody commits to the trunk at least once a day. People who are used to traditional projects thought this was crazy because integration on traditional projects is really, really painful. In fact, some tools in the early 90s and even still today force this model of forcing developers to work in isolation and then force them to merge all of their results in. But what the XP guys realize, and there are a huge classes of problems like this in the software world, that the longer you put them off, the worse they get. And they don't just get worse linearly, they get worse exponentially. It has to do with the combinatorial combination of the way things tangle in the software world, the way things automatically complex to one another, makes it really, really difficult to detangle them when the time comes. And they realize with continuous integration, if we force ourselves to deal with all these little merge conflicts every day or every hour, they never grow into these big, huge things that you have to deal with. In fact, they attack every problem in the XP world like this, find the most painful thing. The thing that's making it painful is because you're trying to put it off. Start doing that a lot more eagerly, and that pain will melt away because you're amortizing all that pain in little tiny bits before it has time to grow up this exponential curve of really, really extreme pain. That's exactly this idea of pulling in deployment stuff into your regular build cycle because that's a really painful thing in a lot of organizations. So the XP guys came up with this idea of continuous integration, that everybody integrates their code at least once a day. But then they almost immediately built mechanisms around this, continuous integration servers, cruise control, and Bamboo, and TeamCity, and all those cool tools. And we think about continuous integration mostly as the tooling now. And a lot of developers got really ambitious with the tooling and said, you know, we're using it to do canonical builds and to run unit tests. Let's get even more ambitious. We can get it to run functional tests, and we can get it to do automated stress testing for performance and scalability testing. We can get tools like Water or Selenium or Sahi to simulate browser-based regression testing by recording and playing back interaction with the browser. And at some point, you get so much confidence in the mechanism that you built around continuous integration that you say, you know, I can't think of any more way to torture my code before we put it live, and so we should just deploy it. And that's this idea of continuous deployment. Deploy is the last stage of continuous integration. And a lot of companies are doing this, particularly companies that are in really, really tightly competitive markets. Because the big metric that we track in the continuous delivery world is this metric of cycle time. That is a measure of mechanical efficiency. That is the amount of time from when you start working on a problem, does it show up in working software. We measure this diligently, and if you're on, so we had a client not too long ago that was on a timed 6-week release cycle, so their cycle time is 6 weeks. We did a relatively small amount of work for them and got their cycle time down to an hour and a half by automating all those processes. What that means, though, is if their competitors are still on a 6-week cycle time, our client can now put out several thousand releases for every one of theirs. So if they're doing something like a marketing campaign, they can iterate over a bunch of different versions until they find one that resonates, whereas their competitors have got to nail it out of the gate exactly right the first time because they have a 6-week penalty box to wait until they get to do it again. At some point, cycle time becomes a competitive advantage, but it's like the famous quote that William Gibson has about the future. He says the future is already here, it's just not evenly distributed. And the exact same thing is true here, that cycle time is incredibly important. It's just more important in some markets than others, but it's becoming important in lots of different markets, which is why people go to the extra engineering effort to do something like continuous deployment and build all that automated sophistication into their build process. But for a lot of big companies, this would cause more churn than benefit, but the idea of continuous delivery is basically the same engineering practices as continuous deployment. You just don't automatically put it live when you're finished. That becomes a business decision as to when this release goes out, but all of the actual engineering work is pretty much the same, this idea that software is always in a deployable state. Because there's this observation that we made in the Agile world that for a long time we focused really heavily on the front end of software development. We focused a lot on doing estimation and doing iterative development and doing test-driven development and tight feedback loops with showcases. But then in a lot of organizations, code moves to a very unagile place where it gets integrated with all the other projects, some agile and some unagile, and then centralized QA, which is sometimes on a different floor or a different building or a different time zone or a different country altogether. And then from there, it goes into its care and feeding and operations for the rest of its life. Operations is a kind of a dark place in many organizations. I can't resist telling my favorite operations story that I saw not too long ago from one of my colleagues had this experience. They were in an operations group for a big company, and they had this computer that had been issued them by a credit card company. And it was running some really flaky version of an operating system, and it crashed all the time, but there was no monitor, no keyboard, they didn't have logins to this box, it was just issued to them. You plug a network cable in, you send it packets, and it sends you back approval codes, and it was really flaky. And so they wanted to figure out a way to automate this machine. And so what they did was, took another physical computer and sat in front of it, and wrote a piece of code on it that pinged this machine to see if it was alive or not. As soon as this faulty machine stopped responding, this machine would eject its CD tray, and they mounted a pencil on the front of the CD tray that hit the power button across from it and recycle that computer. That's innovation in operations. But that's what operations looks like everywhere. It's always duct tape and baling wire and bubble gum. What we realized was you can't have that going on and assume that everything is perfectly nice and stable on the front end when that kind of stuff is happening on the back end. You have to incorporate that into every build. This is this idea of continuous delivery, is all those formal QA processes and all those operational processes you need to do all the time. That's not something you can put off for a long period of time. Code is always in a production-ready state, and business needs trump operational concerns. But what this means is the role of Agile architect just got a lot messier. Because for a long time, architects could kind of ignore all those operational concerns as somebody else's problem. Somebody else is going to have to mount a pencil on the front of a CD tray somewhere. I'm not going to have to deal with that. But now you do have to deal with that because you're going to be doing those operational things every single time you do a build. Every time you make a change to your architecture, this can have possibly an impact on some of these downstream processes, so you have to start thinking about this a lot earlier. A definition of continuous integration is fast automated feedback on the correctness of your application every time there's a change to code. Continuous delivery is similar to this, but broader in two important ways. Continuous delivery is fast automated feedback on the production readiness of your application every time there's a change to code, infrastructure, or configuration. So here we're not just looking at correctness, we're looking at production readiness, which is beyond just correct. Production readiness means that messy things like logging code is in place and that authentication authorization work correctly and is tested, and all those concerns are part of that code, not that it's passed a few unit tests somewhere. And also the triggering mechanism is much broader because now we're saying that anytime there's a change to code, infrastructure, or configuration, what we're viewing software as in the continuous delivery world as a universe, an ecosystem that contains our software, but it also contains everything our software is coupled to, which includes the operating system that it's running on and the database that it uses to get its persistent data. Those are all considered one universe. And anytime something changes in that universe, we want to eagerly try to incorporate that change as quickly as possible. This is part of this philosophy of do things as eagerly as possible rather than as late as possible. If there's a change that operations does because a security patch comes out for an operating system, we want that change triggered back at the developer level as quickly as possible to make sure that we can safely incorporate that change. Part of this is let's do these things as eagerly as we possibly can. And we do that, we automate those things in this continuous delivery world through this concept of a deployment pipeline. And I'm going to show you two stages of the deployment pipeline that pertain particularly to the architect. This is the commit stage, which is just like continuous integration. This mechanism, this deployment pipeline, and there are several tools out in the world that do this. CruiseGo is a free open source tool that does this. There's TeamCity and there's Bamboo and other tools. You can wire up tools like Jenkins to do this as well. The idea that this deployment pipeline is it's a series of gates that you try to achieve success, and once you've achieved success here, you move on to the next one, and it tends to be more sophisticated as you go from left to right. So this is the first stage, which is just like continuous integration, where the mechanism pulls and compiles all your source code based on the changes from version control, runs a bunch of unit tests on them. It assembles those binaries for use later in the pipeline and copies them to the file system, which is called artifact repository here. And then you also run code analysis, PMD, check style, find bugs, kind of code here. This is run against every check-in just like continuous integration. It in fact is like continuous integration plus plus. This builds all those downstream artifacts, the jar files, and all the other things that subsequent stages in the pipeline will use because there's no reason to recompile all that stuff for every stage of the pipeline. And if this fails, you want to fix it right away. Now, in this deployment pipeline world, you'll have a bunch of stages in your deployment pipeline. Each one of those stages represents a higher level of confidence in your code as it moves through that deployment pipeline. But there's one stage in particular that's really, really pertinent to the architect role, which is why I bring it up here. And it's modeled in all the continuous delivery literature as the acceptance stage, but it is this milestone stage that may or may not be acceptance test, but at some point along the way, you'll reach a certain milestone where, and let's say it's modeled here as acceptance test, where it pulls the acceptance test and configuration data from the database for version control, pulls those binaries from the file system, but then the first step here says configure environment. This is the first step in our deployment pipeline where we're going to start relying on tools like Puppet or Chef or Ansible or CF Engine to actually build out the infrastructure our code is going to run on. So it's going to say we need a particular version of Linux and then Apache and Tomcat and 47 jar files on top of it. We'll have a script that builds that up from nothing, so that we know exactly what is in that ecosystem. There's this concept in the continuous delivery world of immutable servers, that you never make a change to the binary of a server. You change the source code and then rebuild the server if you want that server to have a change to it. We're trying to get away from touching binaries a lot in this world because it's very inefficient to do that. We'd much rather change the source code and then regenerate the machines to do that. That's what this configure environment says, is this is the first stage where you take ownership of all the operational parts of your code, build that up programmatically. Then once you've built up that environment, you deploy your code onto it and smoke test it, then run the series of acceptance tests or whatever this stage is for, and then when that's finished, you tear down those machines that you've just built up. These are end-to-end tests in a more production-like environment. That's the goal in continuous delivery is as you get closer and closer to release, you get more and more production-like environments. This is triggered by an upstream success. All downstream tests from here will create their own environments. Once you've hit this milestone, all the machines from here continue doing this and just build more and more elaborate versions of it. This is why, as an architect, in the continuous delivery world, you have to know and be concerned with this operational stuff much, much earlier because this acceptance testing stage is going to be in your universe. This is part of the deployment pipeline managed by the development team. This is not just some operational concern anymore. This is a concern for both operations and architecture and forces them to get together and resolve these concerns a lot earlier than was done traditionally, which is a really good thing because now you're resolving those problems before they fester and become this big combinatorial mess. When you put all this stuff together, this is the kind of traditional picture of the deployment pipeline. The main point here is that notice once you start doing this stage, all the downstream stages continue doing that configure environment stage, programmatically building up infrastructure. What we're trying to do here is untangle the things that in architecture and operations have caused us problems in the past. And the way we're untangling those things is resolving any kinds of conflicts as quickly as we possibly can, as eagerly as we can, rather than putting it off as late as we can. And this has some interesting architectural implications for us as well, because what we can start doing then is start building actually finer grained things and start doing triggering builds at the component level rather than at the application level. In fact, there's a lot of research in the continuous delivery world of doing pipelining components where to make sure that if you do have a system that consists of a bunch of components, you know exactly what order those get built in so that you always have known good states, you avoid things like diamond dependencies, and there are other coupling and cycle problems that you can avoid in this world by building your pipeline with an awareness of how your components are related to one another. So in many ways, the continuous delivery world is trying to untangle the concerns between operations and architecture that always tend to manifest late in the project. By looking at those things much, much earlier, we can resolve those issues and not carry flawed artifacts through this entire process, only to ditch them at the end and have to start over. Another example of things pulling apart and uncomplecting or simplifying out in the world has to do with functional reactive programming, which is really, really popular right now. Functional reactive programming gets you away from this callback hell model where everything has to register callbacks with everything else. Functional reactive programming works like a spreadsheet where you make a change somewhere and the mechanism handles propagating those changes everywhere. So it's basically the observer pattern on steroids. But they've built an entire architecture around this, and part of the goal in this architecture is to untangle all this callback code from all the other stuff that's happening in your application. That allows you to think much more easily and clearly about what's happening with events versus other things that are happening in your application. The functional part of this is really interesting too, because another good example where we're able to simplify things and untangle things has to do with the advent, finally, of functional programming in Java. Now, every platform has the ability to do functional programming. Java's the last holdout, and here's why this is such a big deal. So consider this problem. Let's say you have this problem at work. You're given a list of names, and you are supposed to go through that list of names, eliminate all the ones that are just a single character, make all of them initial capital letters, and then return a comma delimited list of the names that are left over. Now that's actually 3 separate tasks. So one of the ways you could write this in traditional Java is 3 for loops. One to loop through all the names and eliminate the single ones, one to loop through all of them to capitalize them, and one to loop through them to make a comma delimited list. But you never do that because you know it's screamingly inefficient to do that in 3 separate loops, and so you just do one big loop and do all of them together. But the problem with that is it's now harder to understand the problem because everything is complected together. It's all woven together now in one thing. In the Java 8 world, we can get away from this and simplify this greatly by using the stream API, because now we can say, okay, filter them where the name is greater, the length is greater than 1, and then capitalize all of them and then join them all together with a comma. This is untangling the iteration from the problem statement that we're trying to solve, allowing you to think at a higher level of abstraction. This is the real benefit of functional programming, is allowing you to think much closer to the problem you're trying to solve, rather than constantly being down in the details of how things work in these little bitty and very intricate ways. The other beautiful thing about this kind of code is, let's say that your boss comes along and says, hey, you know that cleaning names thing, it's awesome, but we need to scale it a lot higher, so you need to make it multi-threaded. Great, now I've got to pull out my iteration code and start doing synchronized blocks and worrying about deadlocks and all that other stuff. In the Java 8 world, you just switch to a parallel stream rather than a stream, and it's automatically parallelized. Now, you can't be brain dead about this. There's still implications you have to think about in terms of concurrency and what's efficient and other things like that. But once you understand those things, operating at this level of abstraction is a much, much more efficient than operating always at the lowest level of abstraction. What this is allowing us to do is untangle the implementation details from the things that we're trying to get done, and we can now do those with higher order functions and a lot less messy syntax. The last of these complecting examples I'm going to show you is a longer one, but really, really popular right now. And it's this idea of microservice architectures. ThoughtWorks is a company. We're in 13 different countries now. We're about 3,000 people. We have people working on projects everywhere. And we're very curious about kind of brand new topics like this. And so we very recently just did a global summit in London where we gathered up a bunch of people from different regions doing work in this area and had some discussions about what does it mean when we talk about microservice architectures, and some interesting had some interesting insights. My colleague Martin Fowler has just published a series of blog entries about microservice architectures. And I want to talk about this a little bit because in many ways, these microservice architectures, particularly when you look at them through the lens of continuous delivery, are attempts to untangle things that have gotten really tangled up in our architectures and starting treating things as singular things. So let me talk about that for a bit. So when you talk about microservices, you're talking about them in contrast to monolithic applications, where you have multiple things running in the same container. You have databases, you have application servers. Application servers can be running multiple applications within their space. Mostly there to take advantage of shared resources. Goes back to the statement that I had before, that yesterday's best practices are tomorrow's anti-patterns. We invested a lot of time and effort into getting things like application servers and industrial strength database servers to work so we could share all those resources, because we just don't have enough resources to give every single thing we want to do dedicated resources. We need to share thread pools and processing power and hard drive space, because hard drive space is really expensive. But then a weird thing happened. Resources got dirt cheap. In fact, Amazon will now rent you resources for pennies on the dollar if you want. Now our big problem are not resource constraints in many places, it's the coupling that we've introduced to try to avoid the resource constraints. This is yesterday's best practice becoming tomorrow's anti-pattern. The microservices world says, okay, let's not do that. Each one of these modules should run in its own separate process. Let's not share those resources. Let's isolate those things, because when you share those resources, you're now coupling things together at the implementation level. And it's hard to evolve those things independently when they're all coupled together like that. Often organized around business capabilities. There's this interesting phenomenon out of the world called Conway's Law. And Conway's Law says that organizations which produce engineering artifacts tend to create communication structures within the engineering artifacts that replicate the communication structures of the company. So in other words, if you have a bunch of UI specialists and a bunch of middleware specialists and a bunch of DBAs, you will end up with validation code in all three layers of your architecture because of Conway's Law. It's almost inevitable. This level of specialization leads to duplicated and sometimes overlapping kind of code, and you end up with siloed application architectures. If you have a DBA group, you almost certainly have a data layer in your architecture because of Conway's Law. It very often works out that way. And so what we're trying to do in this microservices world is take advantage of Conway's Law and say, okay, that's fine. What we're going to do is build very small cross-functional teams where we have operational people on every team. This is inspired by, so there are a bunch of companies out in the world that are doing this style of work. Netflix is very famous about this, and they talk a lot about it. Amazon apparently has a lot of this kind of stuff going on, but they're very closed-lipped about what's going on inside their walls. But one of the things that seems apparent is that Amazon embraced this rule that says that no project should be larger than can be fed by 2 large pizzas. That's called a 2-pizza team at Amazon. And they made that an iron law at Amazon, so much so that, and they also made each one of the teams responsible for the care and servicing of their service. So if you build a service, you're responsible for the operations of that service. To make that happen on a 2-pizza team, they had to embed operations people on each team. But that's a really good idea, because now any kind of operational concern gets handled immediately because there's someone on the team that knows how to do that. So the microservices world tries to take advantage of Conway's Law by saying, well, let's build microservice teams that mimic the kind of architecture that we want to see running in our ecosystem. There's also a focus in this world on products and not projects. And this is a subtle distinction, but here's the idea. If you've got a team of developers that start working on a project, they get done, they then pass that off to somebody in operations who's responsible for the care and feeding of that thing, and then they move to another project. And forget about that old project you were working on, and so operations people end up having to tape pencils to the front of CD trays and that kind of stuff to avoid these guys. Versus if you're building a product. This product mentality, this is what Amazon adopted was, if you build it, you run it and own it forever. So somebody on your team, if it dies at 3 a.m., gets a pager call. What they realize by doing that is that the people on your team write much higher quality code. If you've got to come in tomorrow morning and bump into your team member that was up all night fixing something that you messed up, you're going to feel pretty bad about that versus somebody in operations is mad at you and I don't even know their name and oh, somebody in operations sent me a nasty ticket. Well, that's terrible. But knowing that person and having lunch with them is going to make you a lot more diligent developer. They discovered that ownership is a really important, very powerful force. And that's exactly the attitude on Amazon. You build it, you own it, and you run it. But there's a product owner for it as well that advocates for other people to use it and advocates for success and tries to expand its footprint because it's a product. It's not just a project. That's an important perspective shift in this world. Another interesting side effect of this microservices world is you tend to do decentralized data management. This is borrowing the ideas from Eric Evans' domain-driven design and this concept of bounded context. In the domain-driven design world, a bounded context says that you have a particular boundary, for example, a customer service, and it owns everything about a customer service, including things like its own persistence mechanism. That's exactly what we try to replicate in this microservices world where we have persistence per service. So a particular service will own its own persistence mechanism, and if anybody else needs that information, it typically happens through messaging. Now, there are cases where you will model this on top of a single physical database for performance considerations or something like that. That's kind of modeled over here, this third picture. For the most part, we want these completely isolated away from one another so that if you change one service, it has no impact on any of the other services because they're no longer coupled at the implementation level. But again, this is an eventual consistency kind of world because one of the advantages of having that monolithic database is you can do transactions across it, but the cost of being able to do those transactions is that it's very difficult to evolve one piece of your code base compared to the others because they're all coupled together through that implementation detail. The other interesting side effect of that is you can now get decentralized governance. One of the reasons you end up using this shared infrastructure is because, well, it's the boat anchor anti-pattern. We spend a lot of money for this application servers and these industrial strength database servers. Thou shalt use it on every project where it makes sense to or not. But in the microservices world, if every service owns their own persistence mechanism, maybe the customer service decides, you know what, we're only ever going to have 2,000 customers and we never have to do any kind of crazy querying. Let's just post up a simple Mongo database instead of the industrial strength Oracle that we typically use for everything else. Because I know for a fact that you can go from basically raw IP address to running instance of Mongo in about 90 seconds flat, and I don't think you can get the first install dialog in Oracle up in 90 seconds flat. So operationally, these NoSQL databases are way easier to deal with. And what if you made a mistake? What if you made a terrible mistake and Mongo's a terrible choice for this and it's just a disaster? That's okay, because I can change it out here for another one and nobody outside my bounded context knows that that even happened. Because I own all my own persistence mechanism, that means I am free to make changes as I need to. What that means is you no longer have to force everybody in the organization to use tools that are not the right size for the problem they're trying to solve just because that's the industrial strength infrastructure we have. We're not suggesting that every team gets to run off and go crazy and pick any kind of tool they want, but what we're suggesting is you can make much more intelligent decisions about the actual nature of the problem you're trying to solve, and you're not hugely penalized if you don't get that answer exactly right, because you've isolated that away from the other parts of your architecture that might be affected by that decision. Another nice thing about the microservices world is it works really, really nicely with infrastructure automation, like this deployment pipeline business, because we want to be able to automate the creation of all these microservices. In fact, it's our opinion that you can't really do a microservices architecture unless you have some automated continuous delivery stuff in place. If you get more than a handful of services and try to manually push those things out and resolve all those dependencies, you'll go crazy. So you want to automate those processes, and of course this works nicely. In the continuous delivery world, these are also designed for failure so that they respond gracefully if they fail. And this is a good example of the kind of architectural considerations that comes into this world, because let's say that, so you'll know the danger if you have multiple services of relying on synchronous communication, because what if one of these services gets really busy and now synchronous communication starts failing? So one of the ways to solve that problem is introduce a cache, so that, or a queue, so that you can queue things up, queue requests up. But if you introduce a centralized queue, now you've coupled your service to the centralized thing, and it's hard to move things around. And so what we tend to do is build a little queue within the service itself, so that when requests come in, it queues them up automatically, and you can monitor that service, and if one of their queue is filling up, you can spin up more versions of the service and be much more responsive to things like real-time scalability concerns, because each one of them is designed for the case of maybe I can't do everything synchronously all the time. You don't wire that into every service, but the services that you care about, you do, and that allows you to do much more aggressive monitoring and understanding about this world, business relevant monitoring about things that are happening, like revenue and number of users, architectural kinds of monitoring to make sure that all the pieces are in place and the correct versions of things have resolved correctly. And also this thing called semantic monitoring. This is something that we started on a bunch of our particularly REST-based projects. One of our architects made the very useful observation that you build all these really cool tests at build time to verify that all your REST stuff works correctly, but that doesn't translate into runtime. What he started doing is taking a subset of the tests that they run at compile time and run them as a monitoring facility at runtime to make sure those assumptions are still the same. We're calling that semantic monitoring. We're actually running some of our tests against the production infrastructure to make sure that those assumptions still hold true after it has gone live to production. These microservices tend to be very small and single responsibility, small enough to fit inside your head, and small enough, in fact, that you don't try to maintain them. The idea is that rather than maintain it, just throw it away and rewrite it, which would be actually simpler than maintaining it because it's only a few dozen lines of code anyway. These things tend to be deployed as containerless and like Unix services, so very often they have an embedded web container inside them like Jetty or Simple Web. They have a main method so that you can have a bunch of them in a directory, a bunch of jar files, and write a little script that tells every one of them, run your main method, and that'll start themselves up and start answering requests at a known location. These are typically packaged as executable jars, and they're installed the same way as you install things from apt or yum, just like you would install HTTP or any other kind of daemon process. You can install these and bundle them up in the same ways. There's a lot of interest in this particular style of architecture out in the world right now, so, went too far there, sorry. So I would encourage you to spend some more time looking at this. There's still a lot of questions about this. This is a great presentation from my colleague James Lewis. He was the co-author of the piece that Martin Fowler wrote on his blog, and he has done a talk at InfoQ last year called Microservices, Java Unix Way, and he talks in great detail about implementation detail. Like, for example, he ended up using Atom plus JSON over HTTP for all of his microservice communication, and he initially thought, this is never going to be fast enough. I'm going to have to switch to a binary protocol at some point. And he realized that it was fast enough. So he ended up just doing everything text-based, even though he thought he would eventually have to switch to binaries. But he waited to find out, and turns out he never had to switch. That's the application of this idea of the last responsible moment. So those are all things about microservice architectures. Obviously, you don't have to do microservice architectures to realize the benefits of a continuous delivery or vice versa, but they really align nicely in a lot of ways, and it shows that it's really hard in this world, in this day and age, to think about architecture and not also start thinking about some of these continuous delivery issues because they're going to come up. And in fact, one of the other things that we're really big on in the continuous delivery world is this kind of synergistic engineering approach, to look at all your tools and make sure that they're pulling you forward rather than hindering you in some way. Because we find a lot of teams over-optimize around a particular tool or practice and end up harming their overall engineering efficiency. A classic example of this that I won't go into in this particular talk are teams that use feature branching and end up creating these really incredible Byzantine branching strategies when they could use something like feature toggles and it would be way, way simpler. But you get caught up in the feature branching as the goal rather than the way to get to the goal. We always want to look at particular tools and make sure that they are meshing well within our goals in the project, because everything interconnects. You can't really separate process from architecture. You can try, but all you're doing there is delaying the interaction between those two things, and the longer you delay that interaction is going to be worse. It's been our experience. A lot of tools that you get offer you a really nice primrose path when you start using them, and they're awesome while you're on that path, but then when you need to step off that path, they get really bad. Let me give you an example of this. So one of my colleagues is this guy named Kent Spillner, one of the most mild-mannered guys you'll ever meet in the world. But back in 2009, he wrote this on his blog, that Maven builds are an infinite cycle of despair that will slowly drag you into the deepest, darkest pits of hell where Maven itself was forged. Now, thank you very much, I'll be here all week. Why would a normally mild-mannered developer get so passionate around a tool? Because all this really is a tool. And it made me start thinking about this, and I realized that Maven is actually a good exemplar of the two broad categories of tools that we have as developers out in the world. And I separate those tools as composable or contextual. So things like Bash are composable, and everybody knows that the idea in Bash is that everything produces text and everything consumes text, and you can build some magical little things just by piecing together parts of a Bash shell. I showed an example of that earlier where I did my command line judo, where I said, give me all the Java source files and then tell me the ones that have this method definition inside them. Versus something like PowerShell, where PowerShell, you're still piping things, but you're piping properties, so it already knows the context of what you're piping, and so some things are easier in PowerShell, but it's not quite as powerful. Things like Rake and Gantt are really good examples of build tools that are composable versus things like Ant or Maven. Pretty much anything with a plug-in API is contextual versus anything that's language-based tends to be composable. Emacs and VI are good examples of composable things versus Eclipse and Visual Studio. I don't know of a single Emacs or VI user that doesn't tweak their environment every week or two in some minor way because they have access to the way that the entire thing works. Whereas I never see anybody modify Eclipse or Visual Studio outside the configuration dialog. While that's possible, it would take you a solid week of research to learn how to build a new window in Eclipse, because you have to understand the entire context of that whole framework before you can start working in it. And Visual Studio, of course, is the same way. Languages tend to be composable and frameworks tend to be not composable. And this is not to say one is inherently better than the other, but you should understand the usefulness of these two paradigms, because when in composable systems, you get less out-of-the-box behavior. But you get better building blocks for future capabilities. So you get greater eventual power, but at the expense of a less initial power. Whereas, and eventually more flexibility. Whereas contextual things, you get more out of the box. Clearly, you get more out of the box with Eclipse than you do for Emacs or VI, but you can't build as much stuff from them. Better contextual intelligence, but less flexibility down the road, and less ability to evolve in ways that you'd like to evolve. Which brings me around to this idea of Dietzler's law. I used to work in a company many, many years ago that did a variety of different kinds of development, and one of the kinds of development we did was Microsoft Access applications for clients. And we eventually shut down the Microsoft Access part of our business because every Access project started out gangbusters and a huge success, and they all ended in utter failure. And we wanted to understand why that was, and Terry Dietzler was the one who ran the Access business, and we ended up codifying Dietzler's law, which I talked about in my book, The Productive Programmer. And what Dietzler's law says is, when you use a tool like, for example, Access, and you look at what the user wants, a tool like Access gets you about 80% there really incredibly fast. So much so that the clients love you. It's incredible how fast you're putting that stuff together. But then the 80 to 90% of what they want is possible but difficult, because now you're having to hack at the tool and get underneath it and use it in a way that it doesn't really want to be used. And so it's possible but ugly. But the last 10% is absolutely impossible. And Dietzler's law is that users always want 100% of what they want, and they're never satisfied with less. This is why we don't have 4GLs anymore. Remember the late 90s, fourth generation languages, all the XBases and FoxPros and Power Builders and Paradox were all the rage. They all eventually suffered from Dietzler's law. You could never get 100% of what your user wanted, and so we all ended up back at general purpose programming languages because of this. It's a very, very powerful thing. Frameworks tend to suffer from Dietzler's law. But then that begs the question, how do you choose tools? Well, very often what you'll do is start with the easiest. And a tool like Maven is a perfect exemplar for this, because when you start with Maven, it's perfect. You've got a brand new project, you download Maven, you put a couple plugins in, it's like this is the best thing ever. Because Maven is opinionated. And when you don't have an opinion, having someone with an opinion around is useful. Because Maven says, you're going to put your project like this. Like, okay, I'm cool with that. And it's very dogmatic. It wants to do things a certain way, which is good, because having too much freedom in the early days is kind of bad. It's very rigid and it's very generic. When you start out brand new projects, you're building a generic thing. But what you find is over time, the things that were advantageous to start becoming disadvantageous. When you start disagreeing with Maven's opinion about things, you can't get it to change its mind no matter how much you hack at it. The dogma that was so useful at first, when you start disagreeing with it, becomes bad. It becomes oppressive. The rigidity of it starts fighting you because you can't make it do the things you want. And as time goes on, by definition, your project becomes less and less generic and more specific, which makes a tool like this less and less possible to make you happy. And so what happens is you will reach a point with a tool like Maven, this tipping point, and once you go over the edge, it will never, ever be wonderful again. And so at this point, you should stop fighting with it. This is a terrible thing that most companies suffer from, the sunk cost fallacy. We've been using Maven on this project for 2 years, and I know everybody on the project wants to go commit axe murder because of it, but we've got 2 years invested in it, and we don't want to stop and you start using something else. But at some point you have to. What you have to realize is that every engineering practice will not live for the entire life of your project. That some things that are very suited for very early greenfield projects are really, really terrible ideas for mature brownfield projects, and you need to shift your engineering practices to match the life cycle of the project that you're in. Maven's an interesting case because there is actually a get-out-of-jail-free card for Maven called Gradle, which is language-based, which means it's composable, but it still lets you use all the Maven artifacts and other sorts of things that you've built up, and so you're not having to abandon a lot of stuff, you're just shifting to a much more flexible world. But very often tools don't have quite that convenient escape hatch, but it is worth going and untangling yourself from a particular tool and building a better tool for the part of the project that you're in. In the metallurgy world, they have this term called malleability. It is able to hammer or press permanently out of shape without breaking or cracking it. And capable of being altered and controlled by outside forces. So in the early days of projects, you want to emphasize malleability. You want to emphasize change and the ability to make changes in your projects. And you always want to tend toward less friction around your engineering practices. But as your project gets older, you need to spend more time with refactoring and restructuring exercises to get the same kind of results. You need to reserve time in your project to do some refactoring and some other kinds of structural changes because you didn't spend a whole bunch of time up front thinking about all those things. Those things will pop up as you go along, so you need to spend a little bit of time working on those things. So plan some escalating efforts toward remedial architecture and design as you go along. This is the trade-off for the reduced upfront effort that you didn't do in this Agile world. There's another term in metallurgy called a Neal, which is to heat to allow to cool slowly in order to remove internal stresses and toughen it. So for greenfield projects, you want to emphasize malleability, but for brownfield projects, you want to emphasize annealing efforts, the hardening and the repairing and the remedial refactoring exercises that will keep your code base strong and allow you to keep evolving over time. This is a subtle distinction, but in the Agile world, we tend to prefer pro and reactive to predictive. We're not trying to predict the future. What we're trying to do is be proactive. Try to apply the last responsible moment to make decisions. Look at things and say, have you reached the end of your life cycle, or should I replace you with something else? Versus trying to predict when that's going to happen. Try as much as you can to remove friction from your engineering practices. Simplify and untangle things that you've got tangled together. Look at the reasons why things are architecturally tangled together and think to yourself, is there a way that I can untangle those things and make the two things much simpler because they're no longer interacting with one another? And over time, evolve. And eventually, of course, deliver. And hopefully, continuously. Thanks very much. Hope you enjoy the rest of the comments. Thanks. Okay.